Hey everyone, welcome to episode 3 of my podcast, Anatomy and Physiology Bit by Bit. My name is Dr. Sullivan, and today I want to talk about cells. So I know that you're probably thinking anatomy and physiology, muscles and bones and organs and all that cool stuff, but really every anatomy and physiology class, just about, starts with cells, or at least has cells in the very beginning, because in order to understand all the organs and tissues and all those good things, you really have to understand the smallest parts that they're made of. And those things are cells. Specifically, since humans are animals, we're going to talk about animal cells. We'll get to that in a second, just a little catch up on some things about the podcast. So it has been going a little bit slowly. I was finally able to figure out how to get the podcast listed in Apple and make it through SoundCloud and have SoundCloud hosted and all that cool stuff. So now you got a couple of episodes at least that are available to you, and I'm going to try to release them every couple of days so you have topics that will keep up with the basic organization of a typical anatomy and physiology course. So that should be helpful. I'm actually traveling again. I'm recording this from a hotel in Chicago. Tomorrow I will be doing 2 separate presentations with local colleges here in Chicago about how to utilize digital technology in their anatomy and physiology classrooms. So that'll be a lot of fun. But for now, if the sound quality is not so hot, it's because I'm sitting in a hotel room with no carpets, kind of weird tile walls, no desk, only a few hangers to hang clothes up, no drawers. It's a really kind of a weird hotel. I won't mention the name, but it's definitely different. So let's get moving with cells. The study of cells is called cytology, Cytology, cytology. Not Scientology, that's Tom Cruise's religion. This is cytology, so keep that separate for sure. This one is the actual science version of that. Cytology is the study of cells. Every living thing that we know of is made of cells and the materials that cells produce. Cells are the smallest units of life that are considered to be alive. And they come in lots of shapes and sizes. You can see flat tile-shaped cells or round cells, square cells, rectangular cells. Some cells look like stars. They all look really different. Some cells are really super long, like a neuron could be a meter long. And then some cells are really, really tiny. Some cells have a nucleus and some don't. So they're very different from each other, but they all come from the same single cell in your body that is derived from the one sperm cell that fertilized the one egg cell that eventually became you. Your embryonic development started with that fertilization. A cell with half of the chromosomes in it fertilized another cell with half the chromosomes in it, and the combination of those chromosomes in that nucleus eventually became a full cell that turned into all of the cells that exist in your body today, just about. So it's kind of interesting the way that happens. Now that you're born, I'm assuming you're born, and fully developed, you've got tens of trillions of cells that all come together, and they individually, with cells that are like them, form tissues. Those cells all develop and differentiate from that single set of stem cells. So those original cells, they had no specialty, they had no special function, they had no special look to them. They're what we'd call stem cells or undifferentiated cells. But eventually, those cells will start to develop and differentiate into skin cells and bone cells and liver cells and kidney cells and all those things, so that way they can have specific functions that they can do in your body. Those cells will come together, or really, I should say, like cells will come together to form tissues, and then those tissues will come together to form the organs and organ systems that do the jobs of your body. But it all starts with cells. And the cells, they have different shapes and sizes and perform all kinds of different tasks. There's cells that secrete hormones. Those are endocrine cells. We've got cells that start off long and then get shorter And that way you can move your joints, and we call those skeletal muscle cells. We have cells that can conduct electrical impulses, like neurons and muscle cells. And the nervous tissue cells and the nervous system cells do all of this electrical activity so that you can experience the universe. So what makes animal cells different from other cells is that the outer boundary of an animal cell is not a wall, it's a membrane. There are two main parts, I should say, to the cell. There's the outer boundary, which we call in animal cells a plasma membrane, and there's the inside called the cytoplasm. And the cytoplasm is a mixture of a lot of different things, like a fluid called cytosol and organelles, which organelles do the individual jobs that all come together so that the cell can do its jobs. You've heard of organelles. They're mitochondria, Golgi complex, endoplasmic reticulum. You've heard of those. We're going to talk about them later. But I want to focus on the plasma membrane for now. It's really what makes us different from plants and bacteria and fungi. Animal cells have an outer boundary that is a membrane, and it's made mostly of lipids, whereas the cell wall of plants, theirs is made mostly of carbohydrates. You've probably heard of cellulose. So our cell membrane, or plasma membrane, is made mostly of lipids and proteins. And I want to talk about that a little bit, and I want to focus on the plasma membrane first. But in order to do that, one thing we have to talk about is a little bit of chemistry. So to get the little chemistry out of the way, I want to talk about different molecules. And some molecules, like water and glucose, are what we call polar. And that means that the charges of the atoms in that molecule are not equally dispersed throughout the molecule. Like part of the molecule is a little bit positive, the other part maybe is a little bit negative, even though the overall charge is equal or zero. Polar molecules are a little weighted towards one side and the other with positives and negatives. And polar molecules are what we call hydrophilic. And that means they have a tendency to mix with or dissolve in or be wetted by water. Some people use the term water loving. And that helps you remember what hydrophilic means. Sometimes you'll see the term water soluble, and they're using that to mean hydrophilic. So some molecules, or polar molecules, are water soluble. But then we also have non-polar molecules, and we call them hydrophobic, which means they have a tendency to repel water and dissolve lipids. Polar molecules do not dissolve in lipids. So if you try to mix a polar molecule with a fat, you know what happens. An example of a polar molecule is water. So think about oil and water. They do not mix. So these are different classes of molecules. I tend to use the term water soluble, lipid soluble because it kind of helps with the context of where we are. And the reason why this is important is because most of the plasma membrane is made of lipids. About 98% of the molecules in our plasma membrane are lipids. 75% of those are called phospholipids, and that means they're lipids with a phosphate group in their molecule. They look kind of like a big round head with two skinny tails. The head is the hydrophilic phosphate group, and the tails are made of hydrophobic fatty acids. Since this molecule, these phospholipids, have a hydrophilic end and a hydrophobic end, we call them amphiphilic. Means that they've got a water-soluble part and a lipid-soluble part. Each plasma membrane of our cells has two layers of these phospholipids. We call it the phospholipid bilayer. And they're arranged based on their affinity for water. And that's because the extracellular fluid outside the cell and the cytosol that is inside the cell are both mainly water. So the hydrophilic heads of the phospholipids face the watery extracellular and intracellular fluids, while the hydrophobic tails face away from the water and toward each other. This creates what's known as that phospholipid bilayer. Since we're on the topic of the lipid bilayer, let's talk about how that applies to the movement of materials into and out of the cell. So the reason why we're so concerned with the hydrophilic or hydrophobic nature of molecules is because the lipid bilayer, or the plasma membrane itself, one of its jobs, in addition to just being the boundary that holds the cytoplasm in, is that it has to regulate the movement of materials into and out of the cell. So that's kind of an important job. Our plasma membranes are said to be selectively permeable. Permeable means allowing liquids or gases to pass through it. That's what permeable means. Since our lipid bilayers are semi-permeable, it means some things can get through and some things can't. So that's kind of a problem. We have to worry about what kind of molecules we need to get into and out of our cells. Are they lipid soluble or are they water soluble? If they're lipid soluble or hydrophobic, they can diffuse right through the plasma membrane because the plasma membrane is all mostly lipids. If they're hydrophilic or water soluble, they can't. They kind of bounce off, unless the molecule is really small, like water and urea. But large polar molecules, like glucose, they can't get through the lipid bilayer on their own. They need some help. All right, so that's why it's really kind of important to understand the chemistry of it, of these hydrophilic and hydrophobic materials, the lipid bilayer, and things like that. But there's more to the plasma membrane than just those phospholipids. Dispersed throughout the bilayer are several different kinds of protein-based structures. We call them membrane proteins. And the membrane proteins, they can either be embedded in the phospholipids, we call those integral proteins, or they could just be kind of floating along the inner or outer surface of the membrane. We call those peripheral proteins. And a lot of these proteins are very functional. They allow the cell to respond to chemical messengers in the area, or they might even allow polar molecules to pass through the lipid bilayer, or they might allow ions to pass through. Ions like sodium ions, potassium ions, chloride ions, they're not permeable through the membrane. So they need help to get through the membrane. And the membrane proteins, that's one of their jobs. And there's a lot of jobs of membrane proteins. We're going to go over a few of them. Now, some of these integral proteins, the ones that are embedded in the phospholipids, they go all the way through so that they have a surface facing the outside of the cell and a surface facing the inside of the cell. We call those transmembrane proteins because they go all the way through the membrane.
Bombas makes the most comfortable socks, underwear, and T-shirts.
Warning, Bombas are so absurdly comfortable you may throw out all your other clothes.
Sorry, do we legally have to say that?
No, this is just how I talk, and I really love my Bombas.
They do feel that good. And they do good, too. One item purchased equals one item donated.
To feel good and do good, go to bombas.com and use code AUDIO for 20% off your first purchase. That's BOMBAS.com and use code AUDIO at checkout.
Okay, so these membrane proteins, they have several functions that are imperative to the cell's overall ability to do its job. And there's different kinds of proteins. So we're going to look at a couple of examples, maybe more than a couple. We're going to look at a few examples of membrane proteins. One kind is receptors. Receptors allow the cell to respond to a chemical messenger that's outside the cell. For example, if you have a receptor for a particular chemical like acetylcholine, which is a neurotransmitter, you'll have a membrane protein in the cell's plasma membrane that will chemically react with that acetylcholine and then cause something to happen in the cell, like maybe an ion channel will open. And if an ion channel opens, that means that ions can now flow through that particular membrane. So those are receptors. We use receptors so that the cells can respond to hormones. We use receptors so that they can respond to neurotransmitters. We use receptors so that they can respond to mechanical stimuli. There's a lot of different things, and receptors are specific. So meaning that a receptor for insulin will not respond to acetylcholine because they're chemically specific and they chemically react in a very particular way so that only that chemical can stimulate. We call those chemicals ligands. Or sometimes you'll hear people say ligand. That's the same thing. So Another type of membrane protein are enzymes. Enzymes can catalyze an array of chemical reactions, including digestion and hormone action. So there's enzymes that catalyze chemical reactions embedded right there in the plasma membrane. So there's lots of things that those enzymes could be doing. Sometimes they're involved in what's called a second messenger system and the production of something called cyclic AMP. So you'll see more of that as your semester goes on, and as this podcast goes on, we will cover those kinds of things. I talked a little bit already about what I mentioned as ion channels, but really we call those channel proteins. And these are like tunnels. And there are tunnels right in the phospholipid bilayer, but they're made of proteins, and they allow things that wouldn't normally be able to get through the phospholipids to get through by going through a tunnel. And we call those channel proteins. They allow water-soluble molecules to pass into and out of the cell. Sometimes they're ion channels and they allow ions to pass through. Sometimes they're aquaporins and they let water pass through in large amounts. We know that water is such a small molecule that it can actually slip through the gaps in the phospholipids in small amounts, but in larger amounts they can go through membrane proteins called aquaporins. Think of the word aqua for water, porin for porous. We also have membrane proteins called carriers that will bind to water-soluble molecules and carry them into and out of a cell. We have cell identity markers. These are membrane proteins that have carbohydrates attached to them, and that carbohydrate forms a surface, a fuzzy coat on the surface of the cell called the glycocalyx. And the reason why they're called cell identity markers is because they have specific antigens on them, which are little chemical markers on the cell that are specific to each individual person or organism. And what it's used for is so that the body's immune system can recognize that cell as part of your body. And that's a really important thing to do because you don't want your immune system attacking you. Your immune system is sending cells that go throughout your body that are there to monitor and see if there's any kind of foreign cell or virus or bacterium in your body that it needs to kill and dismantle so that it doesn't make you sick. That's one of the things your immune system is doing. So what we want to make sure is that your immune system isn't attacking your own cells thinking that they're foreign cells. So your cells have these have this structure called the glycocalyx, which is made out of the carbohydrates sticking off of these membrane proteins and act as cell identity markers to make sure your immune system knows which cells are you and which cells aren't you. What ends up happening is you have these situations where your immune system is attacking your own healthy cells. And that we call an autoimmune disease like lupus or rheumatoid arthritis. And those are bad. So we definitely don't want that happening. Another kind of plasma membrane protein we have are called cell adhesion molecules, or CAMs. And what they do is they form what's called cell junctions. And that's how cells can bind to other cells, and that way they can stick together and form a tissue. They also use it to bind to other extracellular material like the basement membrane. So using these proteins and using the hydrophobic nature of the lipid bilayer, the plasma membrane not only acts, like I said before, to form a boundary for the cell and keep the cytoplasm on the inside, it also regulates the flow of materials in and out. And that's really good too, because we don't want too many sodium ions coming into the cell at the wrong time, or potassium ions leaving at the wrong time, or vice versa. That all has to be regulated to maintain optimal health. So that's the plasma membrane. Just a basic overview of the plasma membrane. It applies in so many different ways throughout our bodies, and what we're going to see throughout the course of this podcast is how much the function of that plasma membrane plays into the function of whole organs and tissues and things like that. It's going to be really, really important. I'm going to end it here at plasma membrane, and I'm going to make the next episode all about the cytoplasm. All right. I hope this was informative for you. I'm really hoping that it helps you get your goal of a B. B or better. That's the goal in A&P. If you're just listening because you're interested in the human body, that's awesome too. So thanks for listening, and I will talk to you next time. Anatomy and Physiology Bit by Bit is a production of Minus 55 Media. Don't forget to check out my Instagram account and my YouTube channel, both called Student Help for AP. I'm posting a lot of stuff on there right now that you can watch and that will hopefully really help you understand this A&P stuff. Very special thank you out to my family, Bucks County Community College, and McGraw-Hill Education, where you can find my tutor video-based textbook alternative Anatomy and Physiology digital suite, already being used by several colleges and universities throughout the United States.